actually see how to do this. Really quite merciful.
数学没有那个，因为这个学期逻辑应该是上2年都没有任何波幅增长，都不招波幅，因为他没钱。对，就大概1个月，大概是2天，2天不到。
现在有2天，
下个我一会儿给他们说。
你不要考1.25，对不起。我这一堂课是没有时间。哦。
Have you seen the exam, the midterm? Yeah. If you have any question, you can ask after the class. That's the only chance you can ask in person. Otherwise, you have to send me an email. And we have no meeting on Thursday. So Thursday will be home exam, take-home exam.
Excuse me. Just as an because today we had midterm exam, is it possible to accept the handwritten?
No.
No, for the last homework. Because I was studying for and I didn't have time to do LaTeX.
So for from Sem 2, you just wrote the solution and take pictures.
I uploaded the handwritten to my iPad. Just as an exemption.
Let me check with the TA because it's just for her to be easy to grade. If what you wrote is not clear to read, that's. But other people. So, how many of you just hand wrote your solution for problem set 2? I see. We have made it clear. It has to be typed.
Can I have just like until tonight to do the LaTeX and upload it?
No, the deadline is deadline. It's just 9:30 a.m. this morning. You didn't ask for an extension, so there's no extension.
No, I didn't ask for extension. I uploaded my answers.
But you just wrote that, right?
And very,
you didn't type.
very clean, because you told me the previous time that if you do it clean, it's possible.
You need to check with the TA if she can read that. Yeah.
I'm checking.
But for the midterm, you have to type it.
Sure.
Okay, so this is the inexact proximal point framework we mentioned last time. Basically, in the algorithm, you need to solve this inclusion and this inequality in one iteration. There may be an oracle, a subroutine to solve for this, and so do this loop iteration by iteration. And lambda k here is a subsize, epsilon k is some inexactness, delta k is a tolerance, sigma here is a scalar that controls the exactness of the solution. And here x to the k is an auxiliary iteration. So let's continue the discussion on the convergence. The first inequality follows from gamma k is underneath phi. This is proved as the first statement in the previous lemma. And the second one is just by the minimality. So this is above the minimum plus a quadratic because this is one strongly convex. Gamma is a linear function, a fine function. And the last one should be due to a previous lemma. This is lemma Simon D in the last lemma. So now let's take x to be x star, and let me just rearrange the term if you get this inequality. The proof of the theorem is quite simple. We just follow this inequality and sum over the iterations. So we will have a telescope sum here. Everything will be cancelled. Only x0 minus star will be left. And we ignore the last term. And then you divide the whole thing. And also we ignore this quadratic term. Then we divide the whole thing by the sum of lambda I, denoted by this capital lambda k. So then we get this convergence rate result. Suppose now you have constant step size, so lambda k is always lambda, and delta k is 0. This usually means the problem is smooth. This because delta k controls the non-smoothness. If delta k is 0, it means the problem is smooth. And sigma controls the smoothness. If sigma is 0, it means the problem is non-smooth. So when the problem is smooth and you take constant step size, then you can recover this result for gradient descent. This is the gradient method convergence rate. So this is also simply by taking the sum and divide the whole thing by this capital K. It's capital lambda K. Capital lambda K is just lambda times K. Now let's see how we can show the proximal gradient or projected gradient as an example of the inexact proximal point framework. So in this case, we will take delta k to be 0 because this is for the smooth case. This is one iteration of the proximal gradient method. And we want to show this iterate really satisfies these two conditions with certain epsilon k, x tilde k, and also this is 0. So we have already choose this delta k to be 0. Right, so let's see how this fits into the framework. From the optimality condition, we can say 0 belongs to Right, this is the optimality condition. It's just 0 belongs to this subdifferential. It's a subdifferential of the whole thing. Well, we take the gradient of the quadratic term and move this to the left. So now let's call this difference between the function and its linearization as epsilon k. Then we can see the proximal gradient is an instance of the inexact proximal point framework with this choice. This is because so what this is saying, let's call this as vk. Let's call this this xk minus 1 minus xk divided by lambda or lambda k as vk. Then what this is saying, phi x, so x to the k is xk. Right? And because epsilon, we choose epsilon k to be fk minus its linearization, so this is really LF. And from here, so what's implied by the inclusion there is this is also vk. Right, this inequality is equivalent to this inclusion. And because of the convexity of f, so we can further bound this one by 5x. And now they are the same. So it means this inclusion implies this one, which is the same as this one. So that one is stronger than this, right? And also, this is automatically satisfied. So this is because this term goes away. This is 0, right? X is x tilde. And delta is just 0. So we just need to check this inequality between this term and this term. because of the smoothness, so here we assume f is f smooth. Because of the smoothness, we know this is bounded by L over 2 xk minus 1 norm square. So this is bounded by L times lambda k. And lambda k is actually lambda. And because we assume lambda is bounded by sigma over L, so this is really bounded by sigma times this difference norm square. And it's exactly the same thing here, right? Because x tilde again is xk. Right, so we show the proximal gradient method is an instance of the inexact proximal point method. Right. Any question? Now let's see how we can, because it's an instance of the framework, so we can use the convergence of the framework to show the convergence of the instance, right? Let's see concretely how we make use of that fact. The first thing we need to note is the proximal gradient method is generates a decreasing sequence in terms of function value. This is some fact we have seen before. Okay, I will not prove this one, but you have seen the function value is decreasing before, so this is as a fact, but you can check it in the previous lectures. So this is true for the proximal gradient or project gradient. This is always true. And so let's now use this corridor because this holds for the case when lambda k is a constant lambda and delta k is 0 for the smooth case. So using this result, we can say because x to the k, right? X to the k is xk. So this is just 5xi. And because the minimum is really the last one. And now we choose lambda to be sigma over L. Right, so now we have L times to sigma k. Sigma is just a constant. So the rate is again 1 over k. Right, this is the one we obtained long time ago for the proximal gradient method. But now you can simply use the general convergence result for the general framework, right? And whenever you show an algorithm is an instance of the framework, you can automatically use the convergence rate result of the framework. Okay, that's the powerfulness of the viewing algorithms as instances of the framework. In the homework, you are going to show the proximal subgradient method is an instance of the framework here. So in that case, you need to take sigma to be 0 and just use this non-smooth term. Now let's talk about something that is more general. So instead of looking for the minimizer of a convex function, we may also be interested in finding a saddle point of a min-max program, or we may also want to find solve the marginal inequality. Those are also convex objects, but they are more general than the minimization. So, but all these problems with convex structure can be modeled as finding the zero in a set. So for the minimization case, this map T can be viewed as the subdifferential of f, right? When you want to minimize f, it's equivalent to find zero in the subdifferential at a certain point. And that point x star is going to be the minimizer. But this T can be more general. It can be for a min-max program, like saddle point, or for variation inequality. In general, we consider this is a point to set map. So map a single point, you can map to multiple points, right? This is not one-to-one. And the graph of T of this map is just this pair x and v for any v in the set T of x. There could be many v's corresponding to one x. So whenever you get confused, you just view this T as partial f. That will be clear. So consider this point to set map T, and we say T is monotone. T is a monotone operator when there are consider this is T, not T tilde. Consider two pairs, xv in graph of T, x to the v tilde in graph of T. Then this inner product is non-negative. In this case, we call T as a monotone operator. And we also have the notion for maximum monotone. This is when T is monotone, and for any monotone T tilde, such that the graph of t tilde contains the graph of t, then we always have t is the same as t tilde. So there is no other monotone operator t tilde that is sort of larger containing t. T is the maximum for all the monotones. Yes.
So should that be a subset or include like an inclusion subset, not a strict? Okay.
So again, whenever you're getting confused about this part, just think about t as the subdifferential of f. So when f is a convex function, then partial f, the subdifferential of f, is a maximum monotone operator. Okay, this is just something general, but because this will be the introduction of this t, this monotone operator, maximum monotone, will be very useful for analyzing the min-max program, the saddle point problem. So this is also like the way we analyze the algorithms. We want to provide a unified treatment, right, to analyze different problems with convex structure. Some simple examples are, the first one, as we mentioned, when f is closed convex function, then the subdifferential is maximum monotone. And the second simple example is when Q is a closed convex function, let's consider the map T as the normal cone of Q, which is also the subdifferential for the indicator function. This is what we have seen before. So this operator is again a monotone, a maximum monotone. You can check by the definition of a normal cone. The set satisfies the monotone property and also can show its maximum monotone. I will leave this as exercises for you, but I'm not going to show the details. So some other examples include saddle point, for example, saddle point problem, variable inequality, those are the objects we are going to see later on, and also the Lagrangian function for the constraint program is also a monotone, maximum monotone operator. So let's look at the algorithm. So when we talk about just the operator, this may look kind of abstract, but when you see the algorithm, that will be very concrete. So the motivation is like this. We begin from looking for the zero in a set. Right? This is like when we solve for the minimizer, we look for the minimizer x star. This is like partial f of x star. Right? If you scale it by a positive lambda, then so this implies this one with lambda is positive, right? And we can also add a z to both sides. So then you're going to have a fixed point. I will show you why this is equal to. So this is actually guaranteed by the following lemma. So this is just to apply the inverse operator to the left-hand side, right? Then you get z. It should be like z belongs to the inverse applied to this z, but this is actually equal to. There's only a unique solution. This is true whenever t is monotone. You don't need maximum monotone. Monotone is just enough. So this lemma is saying that whenever t is monotone and lambda is positive, consider two maps like this, from W1 to Z1, from W2 to Z2. Then you can show that actually this is contracting because lambda one, W1 is like the pre-image, Z1 is like the image, right? So it's, I mean the image of this one, of the inverse map, right? So if you apply the inverse map, you go from Z1 to W1, go from Z2 to W2. Then the distance between the two images are lies now equal to the distance between the two pre-images, right? So this is a contracting map, I mean the inverse mapping. And we can also show actually this map is unique so that you have an equality here, and this further implies there's a unique solution. So the way to think about this is like, suppose this T is like partial f, the subdifferential. F is just some convex function. This is like when you apply the proximal point method. This lambda is actually lambda together with this I. This is like T plus 1 over lambda I. Right? If you scale it, it's just like T plus 1 lambda I. T is like partial f, and this is like the gradient of the quadratic term in your proximal point method. It's like this part, right? Moving it to the right-hand side. This is like the T, and this guy is like the 1 over lambda times I, right? It maps, what it maps is xk or x tilde k. Suppose these two are the same, x tilde is x. Move this one to the right, ignore this xk minus 1. Right, xk over lambda is just the map of this one of xk, right? So think about this, this is like the automatic condition for the proximal point method. Because in the proximal point method, you add a quadratic, it's 1 over lambda strongly convex. So make the problem f plus quadratic to be strongly convex. So that's why you have a unique minimizer, unique solution here. That's the intuition. Because here, what we want to do in this fixed point operation is just to mimic what we do in optimization for the proximal point method. But this is just something general. You have a more general map T here. T can be anything that we listed over there, the 5 options. Okay, so let's interpret these two inclusions. What they are saying is like, because this is really like W2 plus lambda T of W2, right? And so you can move W2 to the left, and you can also do the same operation here. That's why we have these two inclusions, right? And because T is monotone, you can also show lambda T is also monotone when lambda is positive. Right, but the definition of monotone operator, we have this inner product is non-negative. And now let's rearrange the terms. Right, and on this side you can use Cauchy-Schwarz. And you can cancel, suppose W1 is different from W2, so you can cancel just one norm here, and then we have the desired result. Okay, now let's see why this mapping is unique. So assume for the contrary, let's assume we want to show the inverse mapping is unique. So that's the assumption for the contrary, right? Because if you apply the inverse map on Z, this means the inverse map of Z can give you either W1 or W2, and they are different. That's the contrary assumption, right? And so, because we have these two inclusions, we can use this result here. But because these two are the same thing, they are Z. So this is 0. This is really a contradiction, right? So this means the mapping is unique. Since the mapping is unique, you can just reverse this argument. So this is a unique mapping, and hence you have a unique solution for finding the 0. Okay, so the way to solve this 0 is really by following this intuition here, the fixed point iteration. So the usually when you want to solve for the fixed point, what you do is you begin from some maybe some x0, right? And then I apply this iterate. I will assign x1 to be I plus lambda t inverse to x0. And because of the contracting property, if you apply this iteration again and over again, you will really generate a contracting sequence, right? So in general, the sequence would be like xk is I plus lambda t inverse xk minus 1. And you can really show that suppose this t is indeed the subdifferential of f, this is exactly the same as the exact proximal point method. So when t is partial f, these two are equivalent when t is partial f. So then the intuition is like this. We have generalized the proximal point method, the exact one, to this inexact one by relaxing some conditions here, right? By allowing some epsilon k and xk to be different from x tilde k. We allow a few inexactness here, right, to relax the proximal point method. That is for minimizing f. And now we have a more general object, this operator t. And we also have the fixed point iteration, the same as the equivalent to the minimization of the proximal point method. So can we relax this fixed point iteration somehow to mimic the algorithm here, right? That will give you the general inexact proximal point framework. And the answer is yes, we can really generalize it here. So another way to formulate the fixed point iterate. So I will just do a quick sketch of the algorithm. So there is a generalized proximal point method, right? The iteration is like xk minus 1 minus xk over lambda k. Right. These two are equivalent. So this is in general. This is for any point to set mapping T. This is whenever T is partial f. But this is in general. So this is the generalized proximal point method. And let's see how we can somehow relax this one to mimic the algorithm here for the general T. The way we do that is by relaxing first here by allowing some epsilon. There's no partial. So the relaxed version of the general map T is called an enlargement. This is called an epsilon k enlargement. I will give the definition soon. And I think that's it. Here, I want to exclude the boundary case. So that's the generalized one, the generalized IPP framework. I will just generalize the subdifferential, the epsilon subdifferential for phi or f to this epsilon enlargement of the map T. So comparing with the definition of monotone operator T, it just relaxes the zero to be minus epsilon. Epsilon is non-negative. Right, so this is a relaxation. So that it enlarges the graph, right? The graph is, this graph of T. Now let's see the convergence property of this generalized IPP framework. The lemmas that we are going to state is they are quite similar to those for the minimization. But the proof is a little bit more general because we are going to show two types of convergence. One is pointwise, the other is agardic. But previously we only showed the pointwise convergence. This is the counterpart of the first lemma we stated for the convergence analysis of the IPP framework for minimizing f. Right? We have seen all these statements before. The only difference is that previously we defined phi k of x to be the same quantity plus phi of xk. But here we just remove the function value. And previously we showed this, this is underneath some phi function value. But now since we remove the phi here, the phi is also removed in the statement. So this is just 0. And the other two are quite similar, just up to a function value 5 something. That's only because here we have no function value, right? Basically, we are minimizing, we are finding the 0 in a set. There's no function, right? Basically, we are solving the automatic condition, no function involved, so there's no phi. The proof of all these three results will be quite similar to what we had before. I will just do a sketch. First of all, B is easy because this is just a linear in X. This is a quadratic function. Again, you can solve this one exactly to find the xk, and that's xk, and also use this definition of vk. You can show xk is actually the minimizer for this quadratic program. So this is the same as before. B is obvious. Let's see A. So for A, because this vk is the same as this vk, so we know it's in the enlargement, epsilon k enlargement of T. So this is equivalent to say x star is in T inverse of 0 or 0 in T of x star. Right? All these three formula are all these three statements are the same. Right? This is another way to say that. It's just the pair is in the graph. So for this pair in the graph, we actually have just by the definition of the epsilon enlargement. Right, this is just by definition. So, rearrange the term, you will see this is, by definition, this is gamma k of x star. So this is proved. C basically is the same as before. So then the minimum of the whole thing, this function here, or this function, same thing. The minimum of the whole thing equal to this is something we have seen before. And also let's take x to be x tilde k. So we also have this identity in the proof of the previous lemma for minimizing f. And because of the requirement, this inequality here, this is greater than or equal to 1 minus sigma over 2 same proof as before. It's except that we remove the function value of phi. The proof of this one is also similar to the proof of the second lemma for the IPP framework. This is equal to minimum of the whole thing plus so this is this identity is this one here. This holds for any x, and by this result here, we have its 1 minus sigma right, and rearrange the terms here, we recover the desired result. This lemma is new. The following lemma is something that we haven't seen for minimizing f of x. So we define a new quantity called theta k. Theta k is the maximum of two things. So theta k is defined to be the maximum of the two ratios, and we show theta k is bounded by this distance square. So recall we have an inequality requirement in the IPP framework, right? That is xk minus x tilde k. Right. By using the definition of Vk, you can reformulate this norm. And from here, this is less than or equal to square root of sigma times this one, right? So we have lambda k, then by using triangle inequality. Using triangle inequality, we have this inequality here. And also from here, we can also say that 2 lambda k epsilon k by ignoring this quadratic term. Okay, so we have these two results, right? So let's square this one. And moving this term to the left, moving sigma to the left, then we have each of them is bounded by this distance square, right? So the maximum is also bounded by the same thing. So this proof is done. And after this fall break, we're going to continue the convergence analysis of the generalized IPP framework. Okay, if you have any questions about the midterm exam, you can feel free to email me anytime during the exam time. Yes.
So I have one question about problem 4. It's just the what about your project. So what we write here isn't set in stone, right? Like we can potentially change it before the project proposal.
Yeah, yeah. This is not a proposal. This is just to kind of force you to think about it earlier. I think the due date for the proposal should be November 7th.
Right.
Yeah. And we will have no office hour tomorrow. So just quiet exam time. But you can email me anytime.
Will solutions to problem set 2 be posted?
Yeah, we'll post it soon.
You have the survey for the final project. How thorough they are.
So I'm expecting the report to be some at the last note, maybe 5 or 6 pages.
5 or 6 pages?
Yeah, it doesn't have to be very long, but the content should be somehow deep. The result should be somehow deep. You cannot just superficially summarize those papers, maybe using ChatGPT. That's not good.
Okay.
你这次有其他课吗？还有的，已经上完了。哦，已经上完了。我们这个都是 quarter 的，我那边的那个。啊，真的吗？对。快上完了。好神奇啊！大的。要是能这么小跳。
还有要问 by definition
Thank you. I'm glad you could make it today.
Yeah,
Hope you're feeling a little better.
yeah, I think so. These chairs are so confusing. Oh, no, I'm so you're good.
It's different every year. This is